Nexrad or Nexrad is a network of 160 high-resolution S-band Doppler weather radars operated by the National Weather Service, an agency of the National Oceanic and Atmospheric Administration within the United States Department of Commerce, the Federal Aviation Administration within the Department of Transportation, and the U.S. Air Force within the Department of Defense. Its technical name is WSR-88D, which stands for Weather Surveillance Radar, 1988, Doppler. Nexrad detects precipitation and atmospheric movement or wind. It returns data which when processed can be displayed in a mosaic map which shows patterns of precipitation and its movement. The radar system operates in two basic modes, selectable by the operator a slow scanning clear air mode for analyzing air movements when there is little or no activity in the area, and a precipitation mode, with a faster scan for tracking active weather. Nexrad has an increased emphasis on automation, including the use of algorithms and automated volume scans. Deployment. In the 1970s, the U.S. Department of Commerce, Department of Defense and Department of Transportation found the need to replace the existing national radar network, consisting of WSR-74 and WSR-57 radars not utilizing Doppler technology that were respectively developed in 1974 and 1957, to better serve their operational needs. The Joint Doppler Operational Project was formed in 1976 at the National Severe Storms Laboratory to study the usefulness of using Doppler radar to identify severe and tornadic thunderstorms. Tests over the next 3 years, conducted by the National Weather Service and the Air Weather Service Agency of the U.S. Air Force, found that Doppler radar provided much improved early detection of severe thunderstorms. A working group that included the JDOP published a paper providing the concepts for the development and operation of a national weather radar network. In 1979, the Nexrad Joint System Program Office was formed to move forward with the development and deployment of the proposed Nexrad radar network. That year, the NSSL completed a formal report on developing the Nexrad system. When the proposal was presented to the Reagan administration, options were considered to build the radar systems, either allowing corporate bids to build the systems based on the schematics of the previously developed prototype radar or seek contractors to build their own systems using predetermined specifications. The JSPO group opted to select a contractor to develop and produce the radars that would be used for the national network. Radar systems developed by Raytheon and Unisys were tested during the 1980s, however it took 4 years to allow the prospective contractors to develop their proprietary models. Unisys was selected as the contractor, and was awarded a full-scale production contract in January 1990. Installation of an operational prototype was completed in the fall of 1990 in Norman, Oklahoma. The first installation of a WSR-88D for operational use in everyday forecasting was in Sterling, Virginia on June 12, 1992. The last system deployed as part of this installation campaign was installed in North Webster, Indiana on August 30, 1997. In 2011, a single new radar was added at Langley Hill, Washington to better cover the Pacific coast of that area. Other radars also filled gaps in coverage at Evansville, Indiana and Fort Smith, Arkansas following the initial installations. The site locations were strategically chosen to provide the most overlapping coverage between radars in case one failed during a severe weather event. Where possible, they were co-located with NWS weather forecast offices to permit quicker access to maintenance technicians. The Nexrad radars incorporated a number of improvements over the radar systems that were previously in use. The new system provided Doppler velocity, improving tornado prediction ability by detecting any rotation present within the storm at different scan angles. It provided improved resolution and sensitivity, allowing operators to see features such as cold fronts, thunderstorm gust fronts, and mesoscale to even storm scale features of thunderstorms that had never been visible on radar. The Nexrad radars also provided volumetric scans of the atmosphere, allowing operators to interrogate the vertical structure of storms and additionally can act as wind profilers in providing detailed wind information for several kilometers above the radar site. The radars also had a much increased range, allowing detection of weather features at much greater distances from the radar site. WSR-88D development, maintenance, and training are coordinated by the Nexrad Radar Operations Center located at the National Weather Center in Norman, Oklahoma. Scan strategies. Unlike its predecessor, the WSR-88D antenna is not directly controllable by the user. Instead, the radar system continually refreshes its three-dimensional database via one of several predetermined scan patterns. Since the system samples the atmosphere in 3 dimensions, there are many variables that can be changed, depending on the desired output. There are currently 9 volume coverage patterns available to NWS meteorologists. Each VCP is a predefined set of instructions that control antenna rotation speed, elevation angle, transmitter pulse repetition frequency and pulse width. The radar operator chooses from the VCPs based on the type of weather occurring: clear air or light precipitation, VCP 31 and 32, shallow precipitation, VCP 21, convection, VCP 11, 12, 121, 211, 212, and 221. Significant advancements in scanning techniques were instituted in the spring of 2014. These dynamic or adaptive scanning techniques include AVSET and SAILS. Both increased the temporal resolution of scans, AVSET by automatically detecting when precipitation returns drop below a set threshold at a certain height and then scanning at no higher tilts, and SAILS by rescanning the lowest tilt halfway through a volume scan. Volume scans previously required over 4 minutes to complete, and these techniques cut that time by approximately half that span without the need for hardware upgrades. Enhancements Super resolution deployed from March to August 2008, the super resolution upgrade permitted the capability of the radar to produce much higher resolution data. Under legacy resolution, the WSR-88D provides reflectivity data at 1 km by 1 degree to 460 km range, and velocity data at 0.25 km by 1 degree to a range of 230 km. Super resolution provides reflectivity data with a sample size of 0.25 km by 0.5 degree, and increase the range of Doppler velocity data to 300 km. Initially, the increased resolution is only available in the lower scan elevations. Super resolution makes a compromise of slightly decreased noise reduction for a large gain in resolution. The improvement in azimuthal resolution increases the range at which tornadic mesoscale rotations can be detected. This allows for faster lead time on warnings and extends the useful range of the radar. The increased resolution increases the detail of such rotations, giving a more accurate representation of the storm. Along with providing better detail of detected precipitation and other mesoscale features, super resolution also provides additional detail to aid in other severe storm analysis. Super resolution extends the range of velocity data and provides it faster than before, also allowing for faster lead time on potential tornado detection and subsequent warnings. Dual polarization WSR-88D sites across the nation are currently being upgraded to polarimetric radar, which adds vertical polarization to the current horizontal radar waves, in order to more accurately discern what is reflecting the signal. This so-called dual polarization allows the radar to distinguish between rain, hail and snow, something the horizontally polarized radars cannot accurately do. Early trials have shown that rain, ice pellets, snow, hail, birds, insects, and ground clutter all have different signatures with dual polarization, which could mark a significant improvement in forecasting winter storms and severe thunderstorms. The deployment of the dual polarization capability to Nexrad sites began in 2010 and was completed by the summer of 2013. The radar at Vance Air Force Base in Enid, Oklahoma is the first operational WSR-88D to be modified to utilize dual polarization technology. The modified radar went into operation on March 3, 2011. Coverage gaps. WSR-88D has coverage gaps in many parts of the United States, often for terrain or budgetary reasons. Such notable gaps include many portions of the Rocky Mountains, Pierre, South Dakota, portions of northern Texas, large portions of the Nebraska Panhandle, and areas near the borders of the Oklahoma and Texas panhandles. At least one tornado has gone undetected by WSR-88D as a result of such a coverage gap, in Uvalde, Texas, where an EF1 that struck the town in April 2014 was not detected by radar. As a result of the coverage gap, initial reports of tornadic activity were treated with skepticism by the local National Weather Service Forecast Office. It is not likely that additional WSR-88DS will be deployed, as the production line was shut down many years ago, and the National Weather Service faces budgetary concerns. Future enhancements. Phased array beyond dual polarization, the advent of phased array radar will probably be the next major improvement in severe weather detection. Its ability to rapidly scan large areas would give an enormous advantage to radar meteorologists. Any large-scale installation by the NWS is unlikely to occur before 2020. The National Severe Storms Laboratory predicts that a phased array system will eventually replace the current network of WSR-88D radar transmitters. Applications. Usage. Nexrad data is used in multiple ways. It is used by National Weather Service meteorologists and is freely available to users outside of the NWS, including researchers, media, and private citizens. The primary goal of Nexrad data is to aid NWS meteorologists in operational forecasting. The data allows them to accurately track precipitation and anticipate its development and track. More importantly, it allows the meteorologists to track and anticipate severe weather and tornadoes. Combined with ground reports, tornado and severe thunderstorm warnings can be issued to alert the public about dangerous storms. Nexrad data also provides information about rainfall rate and aids in hydrological forecasting. Data is provided to the public in several different forms, the most basic form being graphics published to the NWS website. Data is also available in two similar, but different, raw formats. Available directly from the NWS's Level 3 data, consisting of reduced resolution, low bandwidth base products as well as many derived, post-processed products. Level 2 data consists of only the base products, but at their original resolution. Because of the higher bandwidth costs, Level 2 data is not available directly from the NWS. The NWS distributes this data freely to several top-tier universities which in turn distribute the data to private organizations. Operational locations. See also, Canadian Weather Radar Network, Low-Level Wind Shear Alert System, Terminal Doppler Weather Radar. Notes. References. Atlas, David, Radar in Meteorology, Batten Memorial and 40th Anniversary Radar Meteorology Conference, published by the American Meteorological Society, Boston, 1990, 806 pages, ISBN 0-933876-86-6, AMS code RADMET. External links, Theory of Doppler Weather Radar, Frequently Asked Questions by NOAA, Radar Frequently Asked Questions by Weather Underground, Social and Economic Benefits of Nexrad from NOAA Socioeconomics Website Initiative, Real-Time Data, Nexrad Real-Time Data, National Radar Reflectivity Mosaic FAQs by NOAA. Research, Radar Research and Development by NSSL.